Good afternoon, everyone. My name is Yihan from the National University of Defense Technology. Today, I will present our work-in-progress paper, CVS, a metric for security-aware compilation against the side-channel attacks in edge system on chips. Deep learning compilers are widely used to deploy DNA models on edge devices. Given the same model, a compiler may apply different strategies, such as operator fusing, tailoring, and scheduling. These strategies generate different executables. From a performance perspective, this is expected, but from a security perspective, the important point is that these strategies also receive memory access behavior. On edge systems on chips, memory resources such as DRAM are often shared across processors and accelerators. Therefore, different memory access traces may expose different side-channel signatures. So the question we study is, can we choose compilation strategies that are still efficient, but harder for an attacker to distinguish? We consider a victim processor running a compiled DNA inference on an edge system on chip. At the same time, there is a spy processor co-running on the same system. The spy is unprivileged. It does not need root access, physical access, or access to the victim's address space. Instead, the spy continuously issues memory requests and observes its own memory service behavior. Because the victim and the spy share the DRAM controller, bursty memory access from the victim creates contention. This contention appears as a time series trace observed by the spy. The attacker then uses differences in these traces to infer model behavior. Here we show our code observation. The first row shows the same gem operator executed by different backends, PyTouch, TensorRT, and TVM. Although the high-level operator is the same, the DRAM read and write traces are clearly different. The second row shows the same operator on the different compiler configurations. Again, we see different trace morphologies. Some are highly periodic, some have grouped bursts, and some are flatter. The third row shows that this effect also propagates to full model execution. For the same model, different compilation configurations lead to different global trace structures. This means the side-channel signature is not only determined by the model or the operator, it is also shaped by compilation. Therefore, compilation gives us a new opportunity. We may select configurations that make traces more confusing to the attacker. Running a full end-to-end attack for every compiler configuration is too expensive, so we propose CVS, the confusing variance stalker, as a lightweight proxy. The input to CVS is the set of DRAM read-write traces from operators. CVS measures how distinguishable these traces are from each other. It combines two types of information. First, we use multi-dimension DTW distance to compare the global morphology of traces. DTW is useful because compared executions may have phase shifts or different lengths. Second, we extract local salient features such as peak density, average prominence, and burstiness. These features capture short bursts and that may still be discriminative even after alignment. Then we combine the global DTW distance and the local feature distance. Finally, CVS aggregates this distance use both invariance and mean. The intuition is a security configuration should make operator traces similar on average and uniformly hard to distinguish. Therefore, lower CVS means higher traces confusing and potentially better side-channel resistance. We evaluated whether CVS is a useful proxy. The upper part compares CVS and AER. Here, AER means attack error rate, so higher AER indicates that the attacker makes more mistakes. We observe a clear trend. When CVS decreases, AER increases. Quantitatively, CVS have a strong negative correlation with AER, with Spearman correlation around minus 0.9394. The lower part shows CVS guided compilation. For each backend, we generate candidate configurations and compute CVS. Then we validate it using the actual attacker. The results shows that CVS guided configurations remain closer to the default latency while improving security. On average, CVS guided selection increases AER by 24%, with less than 5% latency overhead. To conclude, this work makes 3 main points. First, compiler optimizations reshape shared resources traces, so compilation is security relevant. Second, CVS provides a lightweight metric to quantify how distinguishable operator traces are under a given compilation strategy. So by selecting lower CVS configurations, we can improve resistance against shared memory side channel attacks while keeping latency overhead small. This suggests that security-aware compilation can be a practical direction for the edge AI deployment. This is still work in progress, so there are several directions for future work. First, we plan broader validation across more attacks, platforms, models, and compile optimizations. Second, we will refine the metric through application studies, comparison with alternative metrics, and sensitivity analysis. Third, we want to better understand how specific optimization, such as fusing, tailoring, scheduling, affect CVS. Finally, we aim to integrate CVS into compile auto-tuning so that security can be considered together with performance tuning configuration search. Thank you for your attention. I'm happy to take any questions.